Good morning, ladies and gentlemen. So I would like to present our presentation. My name is Cervenka from Cervenka Consulting. We are the developer of software Athena, and I will be presenting the work that we have done on the modeling of 3D printing. As Gianluca said, and many of the previous presentations, we think it is important. And well, my presentation focuses more on treating the material really after it has been printed. Yes, we don't deal so much with what's happening with pumping and hardening of the materials. We more focus what happens once it is deposited. So the idea is to be able, of course, to upscale from the laboratory experiments. We don't want to do this approach, trial and error. We thought it would be a good idea to use numerical simulation to predict and validate the structure before they are printed. And the approach we are using is, well, it's based on finite element method using our code Athena. Basically, we are using this printing path, and the printing path that activates the finite elements. Of course, the finite elements need to have time-dependent material properties to account for this early age behavior. Well, we try to put it a little bit farther, or to move it a little bit farther on by actually using the G-code. Yes, so that's what we have recently developed, that you can actually build the model directly from the G-code. So you have the G-code, this gives you the printing path, creates the finite elements. Actually, it can become quite complicated, as you can see in this model, because very often you don't have a single G-code for the whole thing, but you build it by parts, and the G-codes, you have separate G-codes for each part. Then you need to somehow connect them together, make sure that the structure is supported. Well, we are using our concrete model, which is a fracture plastic model, to simulate also this fresh state by using some, the material parameters of the model are time dependent, so that means early on the material is more plastic, then it becomes more brittle. So all the material parameters become time dependent. The model is regularized with using the crack bend approach. That means we regularize the softening behavior depending on the finite element mesh size. And how do we address the evolution of these material properties? Of course, we can define time-dependent functions for each material parameter, like the tensile strength, fracture energy, all of them, but usually you don't have those. They are not available. So of course, if you can measure tensile strength development or compressive strength development in time, that's the best way, but usually you don't have that. So what we most often do when modeling 3D printing, we use the hydration data for the hydration heat development. Out of that, we can define a relationship between the degree of hydration to the compressive strength. Of course, the hydration curves should be adjusted based on the temperature of the environment when you are printing. And then out of the compressive strength, we have some rules in our software how to generate the other parameters. Of course, the rules should be somewhat different if you have a young material than if it is a fully hydrated situation. So we need to move from this phase to this phase. And of course, there is the important thixotropy state, which we try to address by our solid material model, which is, you can say, maybe not the right way how to do it, but basically we are playing some trick that we are saying that even though the hydration is not there, we are introducing some initial compressive strength basically to be able to consider this initial strength of the material, which is due to thixotropy, and later on it is changed to the real strength gained from the hydration products. So now let's go to show some examples. So we start from some laboratory experiments. So first we use this, I think, quite famous paper from Wolf, where he predicted the failure of these tests of cylinders. So we can get a quite good prediction of these. Now I would like to move to a little bit farther, to more complex problem. We also did other predictions of that failure of the fresh paste. But now let's look at the failure of the fully printed structure. So we have this structure, which is kind of a wall with some ribs inside, was tested in the lab. So this is the model. So in this case, actually, we did not use the G-code. Here we really created CAD software and then activated the elements directly. What is interesting is that we have these compressive strength values, even the tensile strength values and the Young's models from the test. Actually, and I want to emphasize, these are the data from the test on the printed concrete, not on the cast concrete. So they already should account for the fact that we are creating the concrete by 3D printing. And still, and we also included the interfaces between the layers, also the interfaces between those vertical connections. Some values, of course, that we need to define some values for these interface properties, and also ideally they should be developing in time. Here is the modeling, and actually we tried also to model the whole construction process. That was where some you see some eccentricities developed. And here's the animation to show also some animations. And then we let the structure rest for some time so that it fully matures, and it is loaded. It is loaded up to failure. And what actually was interesting to observe is that if we use those parameters, which I mentioned before, we obtain and use an idealized model without considering the construction process, the 3D printing process. We obtain this kind of strength. While in the laboratory, the strength was here, so about half of it. And as I said, this is considering the compressive strength of the 3D printed material, which should consider already the fact that the material is being 3D printed. So, but it's still not enough to actually consider such a difference in the strength of the 3D printed specimen. So in order to be able to do that, it was really important to considering the printing process, the shrinkage development and all of that, and the interface, also the stiffness of the interfaces. And then it was possible to recover the correct peak load. However, I want to tell you that we did some fitting, or what the main fitting we did was that actually we adjusted the early age parameters of the concrete to obtain this eccentricity. We said 5 millimeters is maybe something, they didn't measure it yet, unfortunately, in the experiment. We did it after that. So we don't know, but I said, okay, 5 millimeters, this is the limit which they would observe, because they said it was very good. So we said, okay, 5 millimeters should be the limit, and with this limit, it was also possible to obtain such a result. So I would say this is, let's say, unresolved issue that we probably are facing in this community, that I think we've seen very often that actually the strength of the material is somehow lower than you would expect. This is the failure mode, so it was in the end quite similar to what was observed in the experiment. These longer walls, they somehow collapsed. So now I want to go to a little bit bigger structure. So we simulated this structure, which was a kind of simple 3D printed building. They also tested it and printed it in the laboratory, tested the strength of it in the laboratory. Actually, the loading machine was not so big, so we just checked that they cannot break it, so that it is strong enough. So there are no really very good data for this. But anyway, we just use it to really drive now and to present that we can model this 3D process directly from the G-code. So this model you see is very irregular, really created from the G-code directly, and the G-code drives the model development as well as the activation of the finite elements during the simulation. You can see very interestingly, this is the plot of the plastic strains. So you see this bottom part where the printing path is very long. So it takes, so there is a lot of time before the printing head comes to the next point again. So there is relatively lower values of plastic strength that has developed. And here, where the printing path is shorter, you see higher values of plastic strengths. Of course, the highest values of plastic strengths are in this self-supported overhanging opening. And interesting was that if we now increase the printing speed, we can get a collapse. So this is, at this point, a little bit qualitative result, because they, of course, have not tested that in this situation. But, of course, again, it depends very much how well we can identify the material parameters and how they develop in time. So with this, I would like to conclude that we are trying to develop this framework on our software Athena to be able also to simulate this 3D printing of concrete. Initially, we very much focused on stability during the 3D printing. What I'm finding now, actually, that the industry is often more interested in the strength of the final structure. Somehow they are printing simple objects, as was mentioned here, so they don't care if it collapses, they try it again. No time to do some modeling. But they are very much interested more in the final configuration, final structure. It is a big problem because the current codes are not suitable for that or are very difficult to use. So that's where I think there is a big interest currently in the practice. So I thank you for the attention. We also are exhibiting here, so if you want to have more discussions, you are welcome to visit us at the booth, at our booth in the exhibition. So thank you for it.